This is a web-based demonstration that utilizes a number of hoops, Ctron, and partner SDKs to show a complete CAE workflow from CAD file loading to displaying analysis results. First, we import a step file using Hoops Exchange, which is running on a server. Thanks to our Hoops Exchange Parasolid bridge, the CAD data can be directly imported into an active Parasolid session that is also running on a server. Using Parasolid's feature detection, we can remove small features that are not necessary for analysis, like these holes. Again, using feature detection to recognize concave edges within a specified angle range, we can create geometry to simulate fillet welds that will be added during the manufacturing process, which hold these steel plates together. Next, we can select and offset these circular hole edges and imprint them to represent the surface area of the bolts and washers that will be used to secure this part. We will use these newly created faces as constraints for our simulation in the future. We will utilize Parasolid once again to create a block that represents a rubber pad, which is designed to mate against this part. We then use this rubber pad to project and define the region that a load will be applied to during simulation. Now that this boundary condition has been defined, we can delete this temporary geometry. Next, we will create a tool body and then do a Boolean subtraction to disconnect these steel plates so that they are not recognized as one completely fused part. This is a necessary step because these steel plates do not connect to each other without being welded in reality. One of the biggest benefits of having Parasolid integrated into this application is that it allows us to modify the model to match the real 3D object as closely as possible. Now it is time to generate a volumetric mesh, which is accomplished using Ctron mesh. Thanks to our Parasolid Ctron bridge, an intermediate surface mesh can be created from a Parasolid body, which includes Parasolid entity IDs. These IDs will be used to identify mesh elements from Parasolid entities during our solve step. Once the meshes have been created, we can use Ctron Envision to visualize the pre-processed meshes. Ctron Envision is a web-based graphics engine very similar to Hoops Communicator with specific CAE visualization tools. We will switch between these two graphics engines and utilize specialized features within each. For example, once in Envision, you can utilize features like cutting planes to ensure that the shape and size of each tetrahedron element is optimal. Next, we select the surface area that we created earlier using Parasolid, where the bolts and washers will secure the part along the bottom face of the part. We then can apply fixed constraints to these surfaces. Next, we can select the back face that we imprinted using Parasolid and specify this region as the location where a force will be applied. We can specify the force value, the direction of the force, and can also specify what type of material this part will be made of. We can also specify these constraints and load faces to the solver using Parasolid entity IDs. We have now completed all of the necessary steps for pre-processing. Now it's time to run our solve step using Ctron Solve. Ctron Solve can perform linear analysis and can very easily be integrated with our other Ctron products. Now that our solve step has been completed, we can jump back to Ctron Envision to visualize the results. As indicated by the arrow, a high stress concentration is observed. This high stress concentration is due to the fact that the fillet welding is just on one side. There is no weld on the other side of this connection. So we will need to go back and fix this by changing the fillet weld to a groove weld. Since Parasolid is running on the server, and we have a full history of all the modifications made to this model, we can simply utilize Parasolid's built-in session handling to undo the Boolean subtraction that we did earlier. Now we can see the location that will need a design change. We'll delete the extra element and rerun the Boolean subtraction to represent a groove weld as opposed to a fillet weld. We can now create a new surface and volumetric mesh and visualize it using Ctron Envision. Things seem to look good. We have improved our design, so now we can rerun our solve step with the same boundary conditions as before. Now we can see the results of our solve step and things immediately look better. The von Mises stresses are relatively uniform. The stress levels have decreased and the max stress has also decreased from 65 megapascals to 27 megapascals. These results are within the design criteria for this part. We can toggle between different ways of displaying the results and also play an animation showing how the part reacts as the force is applied. We can also turn on a cutting plane while the animation runs to see internally how the part reacts. Since C-Tron Envision allows you to see the internal structure as the animation plays, engineers can gain a very detailed understanding of max stresses and how the part deforms over time by moving the position and direction of the cutting plane to the desired location. The animation can also be paused and run frame by frame to get a more precise look at how the part behaves. In this demo, we use C-Tron Solve to create a downloadable result in Nastran OP2 format. This result can then be opened with the C-Tron Envision desktop-based application, which has C-Tron Access integrated. All of the same functionality that is available on the web is in this desktop application as well. If you would like more information about the C-Tron, Hoops, or Parasolid software development toolkits used in this demo, please visit us at techsoft3d.com. There you can also request a 60-day evaluation of these SDKs and take a deeper look at their features and capabilities.